Hi, welcome back to the Alkene edition playlist in organic chemistry. My name's Kevin Tokoph. Make sure to like the video, subscribe to the channel for future videos and notifications. Thanks a lot. It's very much appreciated. In this video, we're going to go over some thermodynamic principles that are going to sort of explain why we get alkene additions and also eliminations. Now, one important thing here, I have this reaction here, and I go from this simple alkene, ethene, add some HCl, and I can do this addition reaction, which we're going to see in a couple videos, that I can actually add hydrogen and chlorine across the double bond, and I can make what is called chloroethane. Okay, that's an addition reaction. And notice what I'm doing, I'm going from something that has a double bond, something that has a single bond. But I can also do the reverse reaction, and maybe you've picked up on this by now, but if I can basically take this right here with a proton and a leaving group, I can reverse the alkene addition and do an elimination to get back to the double bond, the alkene. Okay, so it turns out that in a lot of cases, through different reagents, but of course, alkene additions are the reverse reactions of eliminations. Okay, at least in terms of this reactant right here and this product. Okay, they're reverse reactions. Okay, now the thermodynamic consideration is how do we control which direction this goes? Because technically you can consider this an equilibrium. Depending on how we use Le Chatelier's principle to our advantage, we can shift the equilibrium towards the addition product if we want to. But sometimes if we don't have the conditions right, Le Chatelier's principle will force it back and do the elimination, and we won't get what we want. Okay, so sometimes you want an elimination, other times you want an addition. And it turns out that the main thermodynamic consideration is temperature. Okay, so what I want you to notice here is that these red bonds right here, this pi bond right here, these are pi electrons right there, okay? And then this sigma bond right here, this sigma bond between the hydrogen and the chlorine atom, those are bonds that are broken. That's why I've indicated them in red. And notice this hydrogen bond to the carbon and this chlorine bond to the carbon, those are bonds that are formed. Now, one thing that's important is if you want to get sort of an estimation on how much energy in the bonds that are broken versus the bonds that are formed in that reaction, then it turns out there's a thermodynamic variable that is used to describe that, and it turns out that is enthalpy, or enthalpy, delta H. So this is what we refer to as enthalpy. Usually people shorten it to just enthalpy, it's easier to say, but the correct pronunciation is enthalpy. Okay, delta H. So delta H is basically the measure of, it's an approximation of the measure of how much energy is released or absorbed in the reaction in terms of bonds being broken and formed. Okay, and the delta H is going to actually help us to predict which way it's going to go, to the alkene or to the addition product. Okay, all right, this is something that comes out of some physical chemistry and some math. Basically, you have this formula here. This is basically the enthalpy equation, that dH is equal to dG plus TdS. Okay. Now, if you're in the context of organic, you've probably seen it written as delta H is equal to delta G plus T delta S. Okay. Now, this is one form of what's referred to as one of the formulas for second law of thermodynamics, or the Gibbs free energy equation. Now, if I want to get it in terms of Gibbs free energy, I need to solve for Gibbs free energy, which is delta G. So I'm going to subtract T delta S from both sides. That's going to cancel it over here. And over on this side, I'm going to get delta H minus T delta S is equal to delta G. Now, what's the importance of basically this form of the equation right there? Okay, what is Gibbs free energy? Because maybe it hasn't been super well defined for you and you don't have as much of an idea what it is. Well, when you're looking at a change in Gibbs free energy, or just most people call it Gibbs energy, most people will just say, oh, it tells you whether it's spontaneous or non-spontaneous, right? Does the reaction proceed as written? But it's a little bit more than that. Delta G is a measure of energy that has capacity to do work. Okay? So if you have energy that's available to do work, could be pressure volume work, or it could be non-pressure volume work. If it can do any kind of work, it is Gibbs free energy. That's the basic way to put it. What is T delta S? Okay, or sometimes they just use delta S. But T delta S, what is that? That is energy that has no capacity to do work. Okay, so T delta S, or the entropic consideration, delta S is entropy. That's the energy that has no capacity to do work. It's sort of like a waste of energy. Because what does the second law of thermodynamics tell us? It tells us that you can have as much energy if you want, but there's a limit on how much of that total energy is available to do work in a system. Okay? In fact, most systems have a very low efficiency, meaning not a lot of it's available to do work. Okay? So Gibbs free energy, measure of the energy that has capacity to do work. T delta S, or the entropic consideration, energy that has no capacity to do work. Well, if you look at this form of the equation right there, what is it telling us? Well, it's telling us that if we add the energy that has the capacity to do work and the energy that doesn't have the capacity to do work, then that should be the total energy change of the reaction, right? Because it's sort of like saying, when you're saying has capacity or doesn't have capacity to do work, it's sort of like saying, if I take all the people on the planet, right, all the people on the planet, and I say, well, some percentage of the people are men and some percentage are women, then if I add the two together, then that should be all the people on the planet, right? That's sort of what this is saying. If I take the energy that has the capacity to do work plus the energy that doesn't, that's the total energy change of that reaction. And the total energy change is delta H, which also happens to be enthalpy and also happens to be a measure of the bond energy change during the reaction. It's a pretty good approximation of that. Okay? And just to give you some sense of this equation, when we rearrange it, we get this delta G is equal to delta H minus T delta S. The reason this is useful is because you're right. The sign of delta G tells us if the reaction as written is spontaneous or not. If it's negative, it's spontaneous. Positive, non-spontaneous. Let's take a look real quick at the units of each of these state variables. Okay? Delta G is oftentimes given in units of joules per mole. Okay, so the joules, you can really use any energy unit you want. Some textbooks will use kilojoules, others you can use joules. There are even some I would say, books that are more on the American side that use kilocalories or calories. That's certainly not the SI unit, but you can certainly use that. You just have to make a conversion to joules. Also, delta H is going to be in units of joules or kilojoules per mole. Delta S is a little bit different. When you're looking at entropy as a state variable by itself without the temperature, only delta S, it's actually in something called joules per mole per Kelvin, meaning that the actual entropy of a reaction is dependent on the temperature. Remember, the amount of energy that has no capacity to do work is dependent on the temperature, okay? And then the temperature is going to be in units of Kelvin. It has to be for this thermodynamic equation to work out. So what happens? Well, if I take delta G, so joules per mole, plus something in Kelvin times entropy, which is joules per mole per Kelvin. Notice that the kelvins cancel out, and I'm adding a joule per mole plus a joule per mole. So delta H over here, that's why it is joule per mole, okay? And that's where that comes from, but that's just sort of an aside, okay? Now, the question is, now how do I predict which side of the reaction is favored? Do I favor the alkene addition or do I favor the elimination? Here is the fact. Alkene additions are favored at low temperature. Eliminations are favored at high temperature, okay? And we'll talk about why that is. So why is that? Well, here's what I'm going to do. I'm going to look at the actual energy from the bonds broken. Remember, those are the red ones I had here. The bonds broken versus the energy of the bonds that are formed. The bonds broken, that has an energy of 166 kcals per mole. The bonds formed, 185 kcals per mole. Okay? So if I want to get an estimate of what delta H is, what I do is I take the bonds broken, and then I subtract off of that the bonds formed in kilocalories per mole. And what I ultimately get is that this is approximately negative 19 kcals per mole. Okay? Notice I'm in kcals here. You can certainly do that. Okay? The only thing I'm concerned about here, don't worry about the units so much. I'm worried about the sign of delta H. So this is for an addition reaction. Notice, this is very important. Normally, if a teacher boxes something, it means it's probably going to end up on the test in some way. My PChem teacher did that. Delta H is less than 0. It's negative for pretty much every addition reaction you're going to see. So for addition reactions, assume delta H is negative. Okay? Now we're going to see why addition reactions or alkene additions are favored at low temperature. Let's find out why that is. So remember, for the reaction to be spontaneous as written, we would ultimately need it to have a negative delta G in that scenario. So remember, alkene additions have a negative delta H. So I want to figure out the sign of delta G. Remember, and I want it to be spontaneous, so that has to be less than 0, right? Delta G equals delta H minus T delta S, which has to be less than 0. So I know delta H is negative, so I'm just going to kind of plug this negative in right there. I don't care what the value is, I just want the sign, right? Now remember, temperature is in Kelvin, and when temperature is in Kelvin, it is always greater than 0. You could say, well, it could be 0, but never for organic. Greater than 0, temperature in Kelvin. So that means, okay, this is going to be a positive number, ultimately, the temperature. So let's suppose now the entropy change is positive, okay? Remember, temperature is negative. So what do I have here? I would have a negative number minus the product of two positive numbers. What's the product of two positive numbers? Any two positive numbers. It's another positive number. So if I was to take a negative number minus a positive number, I don't care what the positive number is. It could be infinite number of numbers. That delta G is always going to be less than 0, because if I take a negative number minus any positive number, 1, 100, a billion, a trillion, infinite number, it's always going to be negative, less than 0. So that means that since delta H is generally negative for addition reactions, and if delta S is positive, then that reaction is always spontaneous. It actually doesn't matter what the temperature is. You can do it at any temperature. But we're going to see now why in the next case, say the entropy is negative, which it is in a lot of cases, we're going to see why temperature should be low for an addition reaction. Okay? So again, delta G is equal to delta H minus T delta S, which we want to be less than 0 so the addition reaction can proceed. Well, I already know delta H is going to be negative, okay? My temperature is positive, right? Temperature is positive, okay? It's a positive number because it's in Kelvin. But what if entropy is negative? Well, then you'd ultimately have a negative number minus another negative number, which means you're technically adding something onto that delta H, which is negative. So the question is, what would happen if the number of T times delta S, what if that number numerically, magnitude, was larger than delta H? Well, then what you would have is you'd have some negative number minus a much more negative number, and that would force delta G to be positive. It'd be sort of like saying this. If I had, say, negative 30 minus negative 50, well, that's negative 30 plus 50. That's equal to 20, which is greater than 0. That can't be the case.
But suppose now instead I had my negative 30, but instead I had, say, a negative 10. Well, then it'd be negative 30 plus 10, which is equal to negative 20, which is less than 0. So this term over here, this negative 30, that's like my delta H. No, I don't want negative. I'm just going to say in general delta H. It's my delta H. Then I have the negative sign. And this thing that's in the parentheses, that's like my T delta S. So what do you see here? Well, if I have this number in the parentheses that has a magnitude larger than delta H, I get something that's greater than 0, and that can't be the case. But if whatever's in the parentheses, in this case it's 10, is smaller in magnitude than delta H, then this T delta S, if this is smaller, then I get a number that's greater than 0 or less than 0, and that's exactly what I want. So the rule in general is that ultimately T delta S has to be more positive than delta H. T delta S has to be more positive than delta H. Notice in this case, negative 10 is more positive than minus 30. Therefore, it will proceed spontaneously as written. Okay? So what that ultimately is going to imply is that the temperature has to be really low. Okay? Because if the temperature is low, that's going to force this term inside the T delta S to be as positive as possible. It can still be a negative number, but it can still be less negative than the delta H, and that's what you want. Okay? In the top case, it turned out to be positive, so whoopee, we're good with that. But if what you get as T delta S is negative, okay, then you want the temperature to be as low as possible so that that whole term T delta S becomes less negative than the delta H, and therefore overall you'll get a delta G less than 0. So here is the critical point right here. Okay, this is what's really important. T delta S must be greater than delta H, meaning it has to be more positive than delta H for addition reactions to be spontaneous. Okay, and that ultimately means low temperature. You want a low temperature for addition reactions to proceed. So when we come back up here, see, where was it? We notice that, again, alkene additions, low temperatures, they're favored. And if you want to do the reverse reaction, again, you have to heat that up. Eliminations require higher temperatures. Okay? So hopefully this made sense. You may have seen a little bit more detail than you were looking for. My whole point here is that alkene additions thermodynamically are favored at low temperatures and eliminations at high temperatures. And hopefully this gives you a good understanding of that. Okay, so again, my name is Kevin Tokoph. Thank you for watching this video. Make sure to like the video. Please subscribe to the channel for future videos and notifications. Thank you, and come back and see us later.